Have you ever wanted to start a fire using only a finger click? A punch? Or maybe just a button? Then you are at the right place, because I'm gonna show to you how to build this amazing gadget. It is small, compact, and it works only with a 1.5 volts battery. And it can light up anything with a super hot electric arc. Let's start first with the circuit. It will have three parts. First, a boost circuit, which is gonna get an input of 0.7 to 5 volts and convert it to 24 volts. Then we're gonna have a control stage, and after that a high voltage stage, which is going to convert the 24 volts to around 5 to 10 kilovolts. Let's take a detailed look at each one of them. This is a bus stage. I have mounted it in a plastic support for all the components. Now let's see the circuit. I'm going to explain in detail how it works. First, we have an inductor, a small inductor like this, in which I have wrapped two coils, one of 100 turns and the other of 30 turns. The end of the 100 turns coil, the primary coil, is connected to the collector of this transistor. It is a 60 volt transistor and 700 milliamp. You can use any NPN transistor, but it is important that the collector emitter breakdown voltage to be higher than the 24 volts that we want to achieve. Another very important thing is that these two coils have to be wound in opposite directions, so that the end of the one is connected to the start of the other one. The start of the feedback coil, the 30 turns one, is connected to the base of the transistor through this 1 kilo ohm resistor and the 100 nanofarad capacitor. So, how does this circuit work? First, a small current comes from the battery and goes through the feedback coil and through the resistor to the base of the transistor. Now, this small current at the base of the transistor allows to flow a much bigger current through the collector coil. But now, this current through the collector coil creates a magnetic field around the ferrite core. This magnetic field starts to expand and increase, and it stores energy inside the ferrite core. But not only that. Being it a changing magnetic field, it will induce a current through the feedback coil and through the capacitor to the base of the transistor. But this opens even more the transistor and makes even more current flow through the primary winding and induces even more current in the feedback winding until the ferrite core of the transistor reaches saturation. Now, at this point, in which the saturation is reached, the magnetic field cannot expand anymore. So, the current through the feedback winding will start to decrease, but this will cause the transistor to close. So, less current will go through the collector coil, and the magnetic field is gonna collapse. But this very fast collapsing magnetic field will induce a current through the collector coil. But this current cannot go anymore through the transistor because it is closed, so the voltage will raise until the current goes through the diode and to the capacitor. Being it a very fast event, you want to use a very fast diode. You can use a Schottky diode, but it has a large leakage current, so the best is an ultra-fast diode. At this point, this circuit can create hundreds of volts, but we don't want such a voltage here. because it's gonna destroy the capacitor or the other steps in the circuit. We want 24 volts. So how are we going to control the voltage? We're gonna use this feedback circuit to stop the converter when the desired voltage is reached. It is composed of a 22 volt Zener diode and a LED diode. So when the desired voltage is reached, we can see it from the LED. But how does this work? When the voltage at this point reaches 24 volts, some small amount of current starts flowing through the Zener diode and the LED. This small current will go to the base of this 2N3904 NPN transistor. But the collector of this transistor is connected to the base of the first transistor. So, when the voltage is reached, the second transistor turns down the first one. That will cause the oscillations to stop. So, the voltage at the capacitor will raise no more. Here is the finished circuit. You can see it is very small and compact. You can see that when I turn it on, the voltage at the output capacitor rises until it reaches around 24 volts. Here you can see the oscillations on the collector of the first transistor and how they stop when the voltage is reached. Now the control stage. For the next step to work, which would be the high voltage stage, it needs two voltages. The 24 volts here and an enable voltage down here. How can we give to the next stage this enable voltage? One way is using a push button, who will connect the 24 volts directly to the enable. But what if we want to control it electronically? We can do it using this PNP transistor. When we pull to ground the base of this transistor, then a small current goes through here and a much bigger current through here. This 10K resistor has the job to maintain the base of the transistor at the same voltage as its emitter, so no current can flow through the collector until we pull the base down to ground. Don't be confused by a PNP transistor. This is the emitter, this is the collector and the base. Now the next stage is the high voltage one. This is what is called a ZVS circuit, zero voltage switching. What makes this topology possible is this LC tank circuit here. The most basic and important characteristics of LC circuits is that they can oscillate and move current from one direction to another hundreds of thousands of times in a second. When the control circuit applies that enable positive voltage to these two resistors, they start conducting current that charges the gates of the MOSFETs. In this case, I have used the IRFP 540 transistor. Now, one of them will switch on first. Let's suppose this one here. That will cause the voltage as the drain of this transistor to go down to zero, but the drain of this transistor is connected through this diode to the gate of the other transistor. This makes the voltage at the gate of the other transistor around 0.7 volts, but at this voltage the transistor is turned off. At this point, some current will start to flow through this inductor and to the center tap of the primary windings to the drain of the transistor that is conducting. The passage of current makes the LC circuit oscillate back and forth, many times in a second. Now, when the voltage at this end of the LC circuit goes to zero, it makes the voltage at the gate of this transistor that is conducting go to zero. That switches off this transistor. And the other one starts to conduct current. But it does so when the voltage across it is 0 volts, so we don't have too much of switching losses. As a result, we will have a sinusoidal voltage at the primary, which is going to be amplified many times at the secondary. The primary is around 10 turns and the secondary more than 400 turns. The value of a capacitor I've used here is around 100 nanofarads. And the diodes here are 1N4148. They are very fast diodes, general diodes. And the values of our resistors here are 390 ohms, both of them. And the gate to source resistors are 3.9 kilo ohms. Here you can see the circuit is very small and simple. In the middle there is that inductor that is used like a choke to prevent the oscillations to go to the supply. Now let's make a test. Okay, very good. It works like intended. Here I'm feeding it with 5 volts and you can see the voltage at the gates of the transistors. They're never turned on at the same time. And here's the voltage across the LC tank. At the end, let's combine all the circuits together and we have this beautiful thing. Or ugly thing, depends on how you see it. Using some plastic sheets, we're gonna make a box for it. And voila! I have used an RCA connector for the trigger input. That goes to the PNP transistor. Now let's close this box and the thing is ready for use and for fun. Can you imagine? It gives 10,000 volts with only a 1.5 volts battery. When I turn it on, it needs a few seconds to charge, and you can see the exact moment when it charges because the LED turns on. Now, not only the arcs are really hot, but they can be controlled precisely. Watch this one now. I have connected it with a microphone and can you see? At the exact moment that the bulb touches the table, the flame turns on. Watch it. At the exact moment. Wait for it. Zack. Okay, thank you very much and please leave a comment.